A log enters the flume at the top of the Sierra Nevada. 54 miles away, it will arrive at a mill in the valley having dropped 4,500 feet, carried by nothing but water and gravity. If the grade is miscalculated even a bit, the entire system backs up. Logs pile, the structure fails. And the men sent to clear the jam do not always come back. Before industrial machinery could move timber at scale, this was the solution. 54 miles of hand-built wooden channel, suspended above cliffs, spanning ravines, built in the 1870s, forgotten within a generation. But what made the flume system so effective? And why did it take decades before anyone understood what it truly demanded of the men who maintained it? In the Sierra Nevada between 1870 and 1910, the demand for timber was extraordinary. The Comstock lode, the vast mining complex beneath the mountains of Nevada, consumed wood at a rate that stripped entire forests. Every mine shaft required timber supports. Every mile of tunnel needed wooden cribbing. Every smelter burned cord after cord of fuel. The timber was in the mountains, the mines were on the other side. Horse teams were too slow, too expensive, and broken by the terrain. James Haynes had spent his working life around timber. He came from Vermont, where the logging trade was old and the methods were established. When he arrived in the Sierra Nevada in the early 1870s, he understood immediately that the solutions that work there would not work here. What Haynes designed was a controlled fall. A V-shaped wooden channel, 54 miles long, engineered to use gravity as a conveyor. The logs would ride the water would ride the slope. Construction began with surveying. Before a single plank was cut, crews walked the slopes measuring grade, the ratio of vertical drop to horizontal distance. Too shallow, and logs would stall and jam. Too steep, and the water would outrun the timber entirely. The channel was built from rough-cut planks formed into a continuous V-shape, typically 2 feet wide at the base. A flat-bottomed channel spreads water thinly and generates friction across a wide surface. The V concentrates water at the center, lifts the logs slightly, and reduces contact between wood and wall. Less friction, more speed, less water required. Trestles carried the flume across ravines. In places, it ran along sheer cliff faces, supported by iron pins driven into the rock. Maintaining the flume was more demanding than building it. Wood expands and contracts with temperature and moisture. Joints open. Seams crack. A flume that loses flow loses function. A log sitting on wet wood without sufficient current will stop, catch the next log behind it, and within minutes create a jam capable of destroying the channel entirely. Crews walk the full length on narrow catwalks, often no wider than a single plank suspended above ravines. They carried oakum and tar for sealing leaks, and when a jam occurred, someone had to go in and break it loose. If the pressure released suddenly, the logs would surge. There was no warning. The sluice gate opens, water enters the channel. A thin sheet at first, then a current, then a flow. The first log is set at the intake. It floats, it moves, it accelerates. By the first mile, it is moving faster than a man can run. By the 10th, faster than a horse. By the time it reaches the mill, 54 miles from where it entered, it is traveling at speeds approaching 60 miles per hour. The flume is alive. As the system matured, operators began sending cut lumber, planks and beams milled at high elevation stations, down the same channels. This required tighter tolerances. A rough log can ride a rough channel. Dressed lumber cannot. Some sections incorporated adjustable gates that controlled water volume and speed. The foreman at the intake made that judgment based on experience, on the weight of the timber, the temperature of the water, the condition of the channel downstream. That judgment could not be mechanized. It lived in the man who made it. By the early 1890s, only a handful of men fully understood how to build and manage a flume of this scale. The knowledge was not written down. It was held by foremen who had walked the lines for years, by crews who had cleared jams in winter on catwalks above 200 feet of open air. When the forests were depleted and the flumes were abandoned, that knowledge went with them. The difference between a competent flume builder and a master is not visible at installation. A well-graded channel and a poorly graded one look identical the day they are completed. The difference appears over time, in the frequency of jams, in the rate of decay, in the number of men sent out in the third winter versus the first. The gap between those two categories is precisely where the danger lived. Per Nygaard, a Norwegian immigrant, was 23 when he died, clearing a jam in the 1880s. Elias Warburton, a bridge foreman, was luckier. He survived an 18-mile ride through a flume after being swept in during a repair. The account was not preserved officially. It survived because someone thought to write it down. The flumes were not monuments. They were infrastructure, built to solve a logistical problem at the lowest possible cost, in the shortest possible time. But what they made possible was the comstock, producing silver and gold that helped finance the Union during the Civil War and fund the construction of San Francisco. By 1910, most of the Great Sierra Nevada flumes were gone, not because they failed, but because the forests that supplied them were exhausted. Once the accessible timber was depleted, the economics collapsed. The railroad offered an alternative that did not depend on water grade or maintenance. The wooden structures were left in place. The mountain reclaimed them. What remained were iron pins in the cliff faces, small marks left by a system that no historical marker commemorates. These flumes worked because someone understood how water moves on a slope, and spent years refining that understanding through observation and correction. Long before industrial logistics reached the High Sierra, the movement of timber across a mountain range depended entirely on these wooden constructions. On the grade, a surveyor chose. On the seal, a maintenance crew applied before winter. On the decision a foreman made when a jam formed and the water was rising. The comstock mines were supplied by a system most Americans have never heard of. The cities built with that timber still stand. The flumes are gone, reduced to iron pins in granite, and occasional notches in cliff faces where trestles once stood. These systems shaped the modern world quietly, one log at a time, across mountains most people never crossed. If you'd like to see more of them documented, consider subscribing, and tell us, which forgotten system should we uncover next?